So we have 7 topical groups, and I'm going to mainly concentrate on 4 of them because they're the ones that are most relevant to the theory overlap. But I will tell you the names of all of them, and the lists of topical group conveners are on this slide. So we have one experimental algorithm parallelization, and one that is very relevant is theory calculations and simulation. That's CompF02. Then machine learning. CompF04 is storage and processing resource access. I'd like to encourage people to think about that. CompF5 is called end user analysis and may be less relevant to theory, but I'm mentioning they have a meeting on Monday. Quantum computing has a lot of overlap with quantum information science within the theory group. And then CompF7, reinterpretation and long-term preservation of data and code. We have not had much theory involvement in this, but people might want to think about this if they have data or code that they want to make sure gets preserved. I did some research into the LOIs that we received, and there were 80 LOIs that list both theory frontier and computational frontier. Among those, 68 listed the theory frontier first, 12 listed the computational frontier first. That may have to do with the way they list things, but then I looked into what's the primary frontier of the 68 that listed theory before computational. The 12 that listed computational first were all, the primary frontier was computational. So the ones that didn't list computational first, theory was 19, energy was 18, cosmic 11, rare and precision 12, neutrino 7, and the others all a smaller number. So that was the primary frontier, but these 68 all listed both theory and computation. So I broke it down along computational lines because I figured you would be better at remembering what the theory frontier numbers are, and I remember better the computational frontier ones. So F2 is the theoretical calculations and simulations, and you see the biggest overlap there is TF5, which is lattice field theory. But there are also very substantial numbers with other groups like TF9 and TF8, TF6, etc. F3 does not have quite as much involvement. That is machine learning, but there's strong overlap with TF7 in particular. And CompF4 is the one where I'd like to encourage people to get involved. I'll talk a little bit more about that later when I go to these particular frontiers. And then CompF6 is our quantum computing. So CompF2, I told you what it is. It's very well organized. There's 6 working groups, and a number of them have strong overlap with theoretical topical groups. So cosmic calculations, and I'm listing for the ones that I did note strong overlap, who's leading the working groups. So cosmic calculations, physics generators, there's quite a few people involved with that. And I tagged 4 different theory frontier topical groups for that. Perturbative calculations has a similar overlap to generators. And then lattice QCD overlaps with, I think, at least 3. Within this computation, CompF2, sorry, there are 117 LOIs, and so not all of them had an overlap with theory. And we expect at least 1 white paper from each of the 6 groups listed above, and more are welcome. So you should give some thought to whether you want to have some input to this group. Okay. Oh, I'm sorry, and I skipped this slide for a moment. These are some of the white papers that we expect, and listed some of the lead authors when I know them. So precision physics computational needs, USQCD 2019 computing. These are a bunch of white papers from USQCD. El-QCD forward-looking expansion. So this is, future computing, informal bootstrap, proposed lattice calculations, cosmology, the vision for generators, vision for neutrino generators in particular, and something from the HEP Software Foundation generators. So they already have something that they've produced. That takes care of Comp F2. Comp F3 is on machine learning. It's popular for both experiment and theory. We heard about that on Thursday from Jesse Thaler. Fiala Shanahan is the theorist who's the Topical Group convener in the computational frontier. Unfortunately, she could not make this meeting. Excuse me. They have a 7-page Google Doc detailing their expected white papers and the lists of authors. It's quite impressive. And I put a link to the Google Doc here, and I singled out 4 of the papers: symmetry group equivariant architectures, applications to lattice field theory, model independent searches for new physics, opportunities for machine learning for HEP researchers. And so I just want to emphasize there are many opportunities for machine learning in theory and experiment. And I hope that the theorists who want to apply this will consider their computing needs and see if they need to have input for us. Comp F4, storage and processing. I told you that there were only 2 LOIs initially presented that involved any theory from Topical Group. So, and they were in for the lattice field theorists. I know lattice field theorists need computing access because I am one. And I hope you will consider whether your science will need computing or storage in the next 5 to 10 years beyond what you think the DOE and NSF, beyond time schedule, that the DOE and NSF need to think about. We heard earlier in this meeting that millions of core hours are needed for some of the perturbative calculations. So don't be shy about letting us know what you need. Quantum computing in the computational frontier has a lot of overlap with quantum information science. There have been meetings between the two, some of which I have attended. Hank Lamb gave a nice talk on quantum simulations earlier in this meeting, and his talk showed some of the overlap with the computational frontier because he spoke about hardware. There are topics within quantum information science that will not be the focus of the computing frontier. There were many LOIs that involved TF1, string theory, quantum gravity, and black holes. And here are some of the white papers that we're expecting. There's one on quantum computing for HEP data analysis, which may not be too theoretical. Quantum networks for HEP, quantum software and tools and test beds for HEP. Quantum simulation of field theories for HEP, definitely an overlap there. Quantum simulation of open systems. Quantum material science research for HEP, doesn't sound particularly theoretical. Tensor networks for HEP, I know that these are theorists. Gravity, black holes, and quantum computing. Simon Catterall and Veronica Hubany are 2 of your Topical Group conveners, so that's going to have a lot of overlap. Machine learning and architectural perspectives for quantum HEP applications. So that combines machine learning and quantum computing. So think about what you want to contribute there. So some of the key issues, well, the computational frontier is not like some of the others. We're not going to build a $2 billion or multi-billion-dollar accelerator. We're going to mostly rely on hardware that industry produces, commodity hardware, but the DOE can have a significant influence on the high end of the industry. Our hardware is going to change during experiments and during long-running theoretical campaigns. The software has a longer lifetime. We need to be able to deal with that. So there have been rapidly evolving programming paradigms and hardware in the last, say, 10 to 15 years, and languages have changed over time. Fortran, C, C++, Python, who knows what's next, Julia, VP, C++, people are doing OpenMP offloads, OpenACC, CUDA. Anyhow, another issue for us is that computing skills are in great demand in industry. We train people, but sometimes they get away from us and go off into industry where they make a lot more money. So some of the key questions, in view of the changing computer architecture, how can we parallelize codes to take advantage of multiple levels of parallelism? Can we deal efficiently with multiple levels of memory and storage? We live in a world of distributed computing. Do we have storage where we need it? This is particularly important for experiment. But as a theorist, I know I'm moving files around the country a lot myself. And then in the longer term, what experiments might be built, what are their computing needs? That's not too pertinent to theory. But we have to know if we can meet those demands. And then I want to focus on the last point on the slide, that HEP may benefit from the aggressively accelerated leadership HPC facilities, but how do we cope with the multiple custom software environments? So the DOE is getting 3 new computers. Well, one of them has arrived, Perlmutter at Lawrence Berkeley Lab, or NERSC, but Aurora and Argonne and Frontier at Oak Ridge will be the 2 new exascale computers. All 3 of those have different GPUs, and hence you have to customize your code to deal with them. So how do we best take advantage of the exciting developments in machine learning and artificial intelligence? Similarly, quantum computing. Might we need our own computing center with multiple experimental computers, particularly for quantum computing? Can the DOE and NSF centers better support our needs for machine learning, AI, and quantum computing projects? That's assuming we're not going to just deal with them ourselves, but the DOE has been asking us to make better use, particularly in the experimental community, than they have in the past, of their high-end computing. How do we develop, collaborate, support, and maintain software? I'm kind of running out of time. Do we have enough physicists with the computing skills we need to develop the software? If not, how do we train people in computing so they have the skills? And one interesting question is whether we need to employ computer scientists, applied mathematicians, and engineers, and have multidisciplinary teams to build our software. Can we afford that? Some of those people make a lot more money than we do. Can we afford not to? Because we lose out on what we need from them. So future plans. I hope I've convinced you that we need your input to the computing frontier. And please get involved if you haven't gotten involved, or continue to stay involved if you have been involved. We have mailing lists, Slack channels. You can find the details on the Snowmass wiki. And then our overall goals to identify computing needs that must be met to achieve success in our science, opportunities to advance and take advantage of machine learning and quantum computing. We know that's going to be a strong part of our report. Research and computing that must be performed to achieve our scientific goals. If there is research and we don't fund it now, we're going to fail in the future. We need to find ways to leverage the large national investments by the DOE and NSF in cyber infrastructure. And finally, we're concerned about the number of personnel we need to develop, support, and maintain our software. So thank you very much for your attention.
Okay, thank you. Are there questions? So there was one thing maybe you could clarify. You mentioned you wanted some input on needs beyond what the DOE or NSF supplies. Were you referring to something else than the supercomputers, or what did you mean by that? What are you looking for?
Well, basically, we want as much input as you can give us as to what your computing needs are going to be in 5 to 10 years from now. So this was organized a little bit differently in Snowmass 2013, but if you're a group that is going to be doing big simulations, or I mean, I'm not dealing with experimentalists right now, I presume, but if you're going to have computing needs that you think won't easily be satisfied under the current allocation programs, or what you foresee is in the future, you should let us know now so we can make that point to the funding agencies. Does that answer your question?
Is this in reference to the supercomputer centers, or is it something else that you're referring to?
Well,
Yeah.
It could be the supercomputer centers. It could be you're saying we need to do quantum computing and we don't have adequate facilities for that, and the centers are focused on classical computing. Our needs won't be met. We will not be able to do our science.
Okay. Yeah, that clarifies it. Thanks.
Yeah.
Any other questions? Anything over there? Michael?
Hi, this is Michael Peskin. I'm a little embarrassed to ask this question because you're really concentrating on the high end of the computational needs. But what about run-of-the-mill theorists? Should we, as a field, have an idea about what the basic training computer education should be for students nowadays? So not to do the extreme of machine learning, but if you want to do something in machine learning, what background should you have? How can you use languages most effectively? You know, you see students running simulations in Mathematica. That doesn't seem to make sense. Can we get a field-wide perspective on what is needed and deliver it to graduate students all over the country?
Well, that's an interesting question, Michael. You know, I've taught computational physics in my own department for many years, so I have my own ideas on what I think my students should learn, which would be how to use Unix, a scripting language, and I have always introduced Mathematica in my classes because I think it's convenient for a lot of calculations people can do. I also want people to be able to use a compiled language. One of my last classes was an undergraduate class that concentrated on Python and didn't assume that people knew how to program. But I'm not really sure if I've answered your question. I think you would like, well, let me back up and remind myself that in my life teaching computational physics, I've also come across a number of reports from the APS and probably AAPT on what computational physics education should be. So it's not specific to high energy, but it is general computational physics, and I can get you some of those report references if you like. So I don't know if I'm answering your question or not. It was an interesting one.
Just one more question, and then we have to move on because of the time.
Hi, I'm Matt Bellis from Siena. I just want to make an advertisement. I think it's in the community frontier, but I think there is something about training, and a big section of that is about computational training. I think right now it's geared towards experimentalists, but maybe this is an opportunity for input from theory for exactly the question that Michael's asking.
Oh, thanks for bringing that up. That subject was kind of wrestled away from us. So that is a good point that they are dealing with it in the community engagement frontier. Thanks again for your attention.
Okay, let's thank Steve again.